Hey everyone, my name is Kevin Fleming. This year I will be serving as the ACS Academic Chief, along with Danny, who will also do a similar review video tomorrow. Today I will be covering a previous exam, and I will also be covering a few multiple choice questions that I got from the ACS Organic Chemistry review. So let's dive right in. So for part 1A, we are asked to give an IUPAC name for this hydrocarbon compound that has several different types of substituents on it. So the first thing that we need to do is that we need to list out, or we need to identify the main or the parent chain. So we have to find the chain that is not only the longest chain, but also the chain that gives you the most number of substituents. And when you do that, you find that this chain gives you that. You can also, because of the symmetry of this these last set of carbons here, you could have also chosen this as the ending to that main chain, but it doesn't matter what you choose. You'll get the same answer. So now that we have identified our parent chain, let's see that we actually find that there are 9 carbons. So this means that our parent chain can be identified as nonene. Let's also try to find our substituents. But before we do that, we actually need to find out our numbering, how we are going to number this main chain. So you find that there are several substituents on the left end of this main chain. There are 2 methyl groups and there is 1 propyl group on the left end of this chain. And when you number these substituents, you want to try to get as many groups to have as low of a numbering as possible. So it's better to number this chain from left to right. So let's go ahead and do that. So now that we've numbered our carbons, we can go ahead and identify our substituents, or to note down their position number. So we find again that there are 2 methyl groups on the left end, specifically at the 3rd carbon. So we can write that down as 3,3-dimethyl. We also find that there is a propyl group at the 4th carbon, so 4-propyl. Lastly, we also find that there is a ethyl group at the 7th carbon. So let's list it as such. Now that we have these 3 substituents and the parent listed out, we're almost there. We can almost list out the name, but we need to find out what order we're going to mention these substituents in. And in order to do that, we have to find the alphabetical order in which we can properly list these. So when we look at the first letter of each of these substituents, there is a E, there is a P, but now it would be tempting to choose D as your first letter to look at. But whenever we are considering alphabetical order, we always ignore the prefix that denotes the number or how much we have of a certain substituent. So we are actually going to focus on M, so M for the methyl. And we will look at the alphabetical order of these letters for these substituents. We find that these substituents should be listed in the following order. So now that we have this order, we can put everything together and get our final name. So let's go ahead and do that. Since 7-ethyl is at the top of this alphabetical arrangement, we list it as 7-ethyl. Our next one is the 3,3-dimethyl, so we go ahead and we write that down as well. Last, we also have the propyl, so the 4 propyl. And then the parent, nonane. So we get our final answer, 7-ethyl, 3,3-dimethyl, 4-propyl nonane. For part B, we are given a molecule that has a cyclohexane ring and a few other potential substituents. And we're asked to give the IUPAC systematic name for that compound. So it's tempting to jump right in and say that the cyclohexane ring is the parent or the main chain part of this compound, but let's make sure that this isn't actually the case. And we can do that by trying to see the length of the main chain of the longest substituent that we have right here, and that would be this complex substituent. So let's draw out that main complex substituent, as you can see. Let me expand it out. So we have this complex substituent, and the first thing we need to do is to identify the longest possible chain of carbons. And for the sake of simplicity, I'll choose this as the main chain. Alternatively, we could have also chosen this because it's equivalent in length, but just to make things simpler, I'll just choose the horizontal chain. So once we have this chain down, we can see that it has 5 carbons, and so that is actually less in length than the length of the cyclohexane ring, which has 6 carbons. So we can say with certainty that the parent in this case is the cyclohexane ring. Now it's time to look at the substituents. And we already have one listed, the complex substituent. So let's take a look at that first. Since we have 5 carbons in the main chain, the parent part of that would be a pentyl. And the two substituents, well, first let's list out the numbering of this chain, right? Since we're starting from the carbon closest to the cyclohexane ring, we can number it like this. So we have this numbering, and using this numbering, we find that there are 2 methyl groups, one on carbon 3 and one on carbon 4. So with that in mind, we can write out how we would describe this arrangement of methyl groups on the complex substituent. 3,4 dimethyl. So now that we have that, we can combine the two parts, the substituents and the parent part, and it gives us the name of the complex substituent. (3,4-dimethyl-pentyl). And we'll also list the other substituent attached to the ring, an ethyl group. Now the part of the question that we're dealing with is how are we going to order these substituents in our name, in our final name. So I had mentioned earlier that we ignore the di, tri prefixes when we're considering name ordering, but there is a small caveat to that, and that is complex substituents. When we're dealing with complex substituents, we actually do take the prefixes into consideration. So with that in mind, we can say that the letters that we are going to use from each of these substituents to see their alphabetical order is the D for the dimethylpentyl substituent and E from the ethyl. So when we look at that ordering, we see that we would actually end up putting the complex substituent first and then the ethyl substituent afterwards. And when you look at the cyclohexane molecule, that means that we can number the complex substituent as our first substituent. And now that we have this defined as our reference, that means that the next substituent would be our following substituent, so that would be number 2. In that scenario, if we list it out, we would get a final name of 1,3,4 dimethyl pentyl to ethyl cyclohexane. And this would be our final answer. For part C, we are asked to draw the structure of the following compound. And we have to, before we go any further, we have to break this name down into easier parts that we can process, and then we can finally draw the structure. So I'm going to underline this name, the significant portions of this name that actually give us a clue about how to even start this. So the first thing is the trans. This indicates the stereochemistry of this compound. So the two substituents that we have here, the 1-isopentyl and the 3,2,2-dimethylbutyl, these two substituents on the ring, because they have a trans stereochemistry, that means that one is going to be going into the page and one is going to be going out of the page. So that means that both of them are not going to be on the same side of the ring. So if you were to consider the ring, or the cyclopentane ring, as a flat surface, then one of those substituents would be above the plane in which the ring exists, and another one would be below the ring. So with that in mind, let's just note everything down. So the stereochem, or the stereochemistry, is trans. The substituents are trans to each other. And our parent chain is cyclopentane. And let's just draw out how our substituents would look like. 1-isopentyl would look like the following. Instead of having 5 carbons in one straight chain, we take one of these carbons at the end and we move it up by 1 carbon, and we get this isopentyl. And now let's also draw out the 2,2-dimethylbutyl complex substituent. So when we do that, we find that this is the drawing, or this is how we should depict the dimethylbutyl, right? Because let's see, what's our main parent chain here? 1, 2, 3, 4. It is a butyl substituent. And we notice that there are 2 methyl substituents on the second carbon. So that is why it's 2,2-dimethylbutyl. So now that we have all this info, we can go ahead and draw our structure. So when we do that, we start off with our parent, right? We start off with the cyclopentane. And since they are trans to each other, one has to be going out of the page and one has to be going into the page. So here's where we use wedge and dash notation. So the wedge will be for a substituent that's going out of the page, and the dash will be for a substituent that's going into the page. So it is arbitrary, you can choose one, but the other one has to be the opposite. But for isopentyl, I will say that this will be wedge. This will have a wedge. So we can draw a wedge between the carbon of the cyclopentane main chain and the first carbon of the isopentyl. So when we do that, we have our first carbon here, and we can connect that to our second carbon, and then our third carbon, and then the branch, right? The branch that you see in the drawing below. So you might, again, the squiggly line is just to indicate where we are, right? So these two squiggly lines would be equivalent to each other. So now that we have the first substituent down, let's add the second substituent. So let me just erase this. Oh no, okay, let me try it again. So let's go ahead and draw our next substituent. Since this is 1 isopentyl and 3 2,2-dimethylbutyl, this would be our first carbon, second, and then our third. So in order to actually list out the next one, we need to put this on the third carbon. And since we chose the first one to be wedge, the third one the other substituent has to be a dash. So we are going to connect the cyclopentane ring to the first carbon of the dimethylbutyl using a dash. So let's go ahead and do that. So now we have our first connection, and now let's draw out the rest of the complex substituent. So if you look at this and this, you find that the wedge is only used to connect the cyclopentane ring to the first carbon of that substituent. And the same principle applies to the isopentyl substituent as well. So when you're showing stereochemistry, make sure to only show the wedge and dash notation when you're connecting the parent chain to the first carbon of that substituent that has a certain stereochemistry. And with that, we have our final answer. Make sure to remove the squiggly line that you see at the top next to the dash, to the wedge notation. But aside from that, we have reached our final answer for this question. For question number 2, we are asked to list the following alkanes by order of their boiling point. So in order to do this, there are a few things that we need to take into consideration. So when it comes to evaluating the boiling point, we have to consider intermolecular forces. And specifically, since we're dealing with a alkane for which there are no dipole-dipole moments or any sort of permanent dipoles present, we are dealing with dispersion forces. And dispersion forces can vary in a compound by two primary factors: the molecular weight and the surface area of that compound. So let's examine this. So for the compound on the left, we have how many carbons? We have 1, 2, 3, 4, 5, 6, 7. We have 7 carbons for the one on the left. 1, 2, 3, 4, 5, 6, 7. 7 carbons here on the middle as well. And on the right we have 1, 2, 3, 4, 5, 6, 7. 7 carbons as well. So these all have 7 carbons. And so their molecular weight is not a considerable factor as much as their surface area. Because if you look at these compounds, they have, some are more stretched out, not stretched out, but have longer surface area, while some are smaller. So when we look at this, a convenient way to do this is actually to actually find the main chain of each of these compounds and to find the number of substituents that they have. So let's go ahead and do that. For the compound on the left, we have a main chain that runs down the middle, and we find that there are 3 substituents. So if we write this down, we have, for the parent chain, we have 4 carbons, and we have 3 substituents. For the structure in the middle, we have this as our longest parent chain. We have 6 carbons, and we have 1 substituent. Lastly, for the compound on the right, we have 5 carbons in our parent chain, and we have 2 substituents. So what do we find from this? We see that even though there are 7 substituents and the number of carbons here from the parent and the substituents for all of them add up to 7 because all the substituents are methyl groups, we find that the middle carbon has the largest surface area because the parent chain is very much spread out, and that's why it has the highest number of carbons in the parent chain, and it has the least number of substituents. So as a general principle, you can see that for alkanes, as the main chain increases in length and you have less and less substituents, the surface area of the molecule increases. And this actually means that your dispersion forces increase as well, causing the boiling point to increase. So with this principle in mind, we can actually list out the order already for all 3 of these. So we find that since this has the largest parent chain with the least number of substituents, it has the highest surface area. So we can list this as having the highest boiling point. The compound on the right has the second longest parent chain, and 2 substituents, and so it's more spread out than the compound on the left. So that means that it has the second highest surface area, so it would have the second highest boiling point. Lastly, we would have the compound on the left. And we were able to compare these compounds on the basis of surface area because we knew that their molecular weight would be similar, so we would have to examine their boiling points, their surface area instead as the main factor to evaluate how much their boiling points would vary by, qualitatively speaking. So this is our final answer for part 2. For question 3, we are asked to determine the formal charge of these 2 compounds. So the equation for evaluating the formal charge of an atom is the number of valence electrons that you would have in a compound, or in a specific atom, and that can be determined from the periodic table, as you all know. And from that number, you subtract the number of atoms that you find in the lone pairs. So atoms in the lone pairs. Lastly, you also subtract you subtract an electron for every bond or sigma bond that you have, or every bond that you have. So number, or 1/2 of the number of bonds you have. Sorry about that. Okay, so you can use this equation, but I find it simpler to consider the number of valence electrons and then just take off almost, you can almost imagine in your head in a way, you can consider, so you have, for example, for the left molecule, carbon, you have 4 valence electrons, and you can subtract from that 2 lone pairs, so now you have 2, and if you take away 1 electron from each of these bonds, you also take another 2. So what you're left with is 4 minus 2 from the lone pairs, and 1 from each of the 2 bonds, so that would be another minus 2, and that leaves you with a formal charge of 0. The same principle applies for the compound on the right. So we're examining nitrogen. Nitrogen has 5 valence electrons, and so we are start off with 5. There are no lone pairs, and if you just carve out half of each bond that's connected to nitrogen, you are left with 4. You have to subtract 4 from the expression so far, and you're left with 1. It's simply the formula, but instead of actually writing down the formula and constantly manually computing it every time, if you do enough practice and you're able to see the structure and you can, just mentally cleave out each of the bonds that are attached to the atom of interest, then you're able to get that formal charge quick, which can actually help you a lot whenever you go on to learn more difficult concepts covered later in the course. So we are left with the formal charge of +1. For number 4, we are asked to draw all the structural isomers resulting from the monobromination of this compound. So before we actually go and solve this problem, we should just take a look at this molecule first. So we find that there is actually a lot of symmetry in this molecule, right? So having a molecule here, or substituent here, is the same as having a substituent here. If you just rotate it, you end up in the same position, right? So due to that symmetry, you have to be careful not to actually draw duplicate structures when you're considering the monobromination of this compound. So there are actually 3 unique sites in this material, right? 1, 2, and 3. So, because if you add, for example, if you were to also consider this point, by symmetry, these 2 points are actually equal. So whenever you draw out the monobrominated structure, they would just be identical. You could just flip them and you would get returned back to one or the other. So you would just have a duplicate structure. So you don't want that. And the problem clearly states that as well. So there are only 3 unique positions in this compound that you can actually insert a bromine, and you would actually get different compounds, 3 different structural isomers, right? And structural isomers are compounds that have the same molecular formula, but the thing is that they differ in the connectivity between the different atoms. So we don't want duplicate structures. And you can just try this out on your own. Maybe you try adding a bromine here and here, and if you rotate it, you can just see that they're essentially the same structure, but you just moved it around. You just rotate it around. So you don't have structural isomers at that point. So that is why we are left with just these 3 unique spots on the molecule to brominate. And when we do that, we get 3 unique products. And these are our final answers. For number 5, we are asked to determine the polarity of these two compounds in A and B. And so the first thing that we have to do is that we have to actually draw out the structure, because the polarity of a compound is essentially determined by the net dipole moment. And the net dipole moment is determined by the sum of the individual dipoles in the molecule. And the sum of the individual dipoles in the molecule are affected by the geometry of the molecule. So in order to evaluate the geometry of the molecule, we need to actually draw out its full geometric structure. So the first compound that we have is actually dibromomethane. So let's draw this compound out. Since the central atom is carbon, you can draw the carbon in the center here. And let's draw the substituents that are attached to the carbon. And since this has carbon is attached to 2 hydrogens and 2 bromines, it would have a tetrahedral structure because of sp3 hybridization. So I'm just going to also incorporate the wedge and dash notation here to indicate the tetrahedral structure. Tetrahedral structure. So because of this, we know that for an sp3 bond, the bonds are 109.5, and if we had 2 hydrogen atoms in place of the bromine, there would essentially be no dipole moment for 2 reasons. One is that the CH dipole moment is pretty negligible, and also the sum of the dipole moments, because of if there was even if there was a very small dipole moment from the carbon to the hydrogen, they would all cancel out by the virtue of their geometry. But in this case, the same principle doesn't apply. So let's just draw out our vectors, right? So we can ignore the dipole moments for the CH bonds because they're pretty much negligible. And since the carbon is the less electronegative atom, when we draw out these dipole moments, the net dipole moment of this molecule proceeds in this direction in space. So that means that it is not nonpolar because the compound does not have a 0 dipole moment. So we can list the compound in A as polar. For part B, we have CO2, carbon dioxide. So when we draw out this molecule, draw out the Lewis structure, we draw the 4 bonds connected to carbon to give it a formal charge of 0. Since this carbon is electrically neutral, the CO2 is electrically neutral, we get this structure. And when we draw the dipole moments, the first ones we should consider are the ones between the carbon and the oxygen. So because CO2 is a linear molecule, these 2 dipole moments, they cancel each other out. So that gives us a 0 dipole moment caused by these 2 individual dipole moments between the CO bonds. Well, then you might be asking, what about the lone pairs? What about the dipoles that they produce? So let's draw that out. So the net dipole from the left and the right sides is as such. But because there are two lone pairs on each end, and they're going in opposite directions, these two vectors cancel out. So again, we are still left with a zero dipole moment. So this means that our molecule has a zero total dipole moment. So we are left with a nonpolar compound. For question 6, we are asked to rank these hydrogens in this molecule as in order of increasing acidity. So when we do that, the first thing we have to consider is that acidity, especially from a perspective in organic chemistry, is determined by the stability of the conjugate base. So as the stability of the conjugate base, goes up, this gives us higher acidity. So this is the guiding principle that we will use to solve this problem. So let's first examine the carbon on the right, because it is the easiest to solve. So when we are considering the conjugate base, we would remove one proton, right? And because we have an acid, right, when we lose that proton to some other sort of base, the protons that are attached to that hydrogen go back to the carbon that was originally attached to that hydrogen. So when we draw out the conjugate base that results from the deprotonation of one of these three hydrogens, we get the following structure. I'm just going to simplify it a little bit by just writing Me for the methyl substituent on the left-hand side. And we have a pair of electrons that originally belonged to that CH bond, but now it's moved on to the carbon, giving it a negative formal charge. And when you look at this conjugate base, one of the main indicators you could use to see the stability of a conjugate base, although there are others, is whether or not it contains resonance structures. And in this case, there are no possible resonance structures that you can have, because you cannot transfer the electrons anywhere else in this compound. You can't transfer this negative charge anywhere. So you can't move it here because it already has, that would violate the octet rule for this carbon because it's already bound to two hydrogens. And resonance structures, they don't change the connectivity of the bonds in the molecule. All you're doing is moving the electrons around. So if you basically break the connectivity, you don't have resonance structures anymore, right? So that means that this structure has zero resonance structures. So we'll just note that down. Zero resonance structures. Now let's examine the hydrogen in the middle of the molecule. If we deprotonate the hydrogen in the middle of the molecule, we end up with this compound. So now this is an interesting situation because now we have a negative charge that is situated between two carbonyl groups. So this, let me draw in the lone pairs on the oxygens. This negative charge on the carbon can actually travel to either one of these two, can actually move to the left or to the right. And that gives us actually two possible resonance structures. So let me draw the first resonance structure. What we get is, just a sec. What we get, if we move the electrons, say, to the left, we get this structure. We form a double bond with the neighboring carbon, and we move the electrons attached to, in the CO bond, we move that to the oxygen because we don't want to violate the octet rule for this carbon. And we continue that for, well, we just leave the right side the same. So we have one resonance structure there, and if we do that again for another resonance structure, if we move the electrons from, instead of the left side now, if we move them to the right side, we get another resonance structure. I'm just going to denote the right side by the ethyl substituent. So we have two possible resonance structures, right? So let's note that down. Just going to say 2 here. So we have 0 on the right and 2 in the middle. Finally, let's evaluate the structure on the left. If we deprotonate one of these hydrogens, we get the following. Or wait, let me draw the conjugate base first. My apologies. Again, I'm using ethyl for the right side. So now we have this negative formal charge here. And unlike in our previous situation, it's not situated between two carbonyl groups. So we're only able to do resonance with one carbonyl structure. So let's go ahead and move the electrons around. When we do that, we get the following resonance structure. And there is no other way to do another resonance structure. So this leaves us with just one resonance structure. For the conjugate base of this compound here. So what this tells us is that since there are two resonance structures for the conjugate base that would result from the deprotonation of one of these hydrogens, that means that that conjugate base would be the most stable conjugate base. So this would mean that the acid from which that conjugate base originated from, so this molecule, would be the most acidic at this hydrogen. So that means that we should note this as 3. And since there's one resonance structure here, it is less stable, the conjugate base would be less stable because only one resonance structure exists. So there would be less stability conferred to that conjugate base due to resonance. So we have the second most acidic. Lastly, for the hydrogen on the right, since there are 0 resonance structures, the conjugate base of this molecule would be the least stable. So at that point, it would be the least acidic. And with that, we have solved this problem. For question number 7, we are asked to find the products of this acid-base reaction and determine the direction of the equilibrium of this acid-base reaction. So let's start off by listing out, or to draw out the full form of these reagents, the Lewis structures. So when we do that, we get the following. So the sodium is considered as a spectator ion here, so it would not be considered, but it would still be shown as one of the final, it would be still be shown in the products, but it just went along for the ride in the reaction, but it didn't actually contribute to any chemical change. So when we consider this, we need to first identify what is our Lewis acid and our Lewis base. So from this, examining these two, we find that the hydroxide ion is actually the Lewis base in this case, because it is negatively charged, the hydroxide is negatively charged, and it's in a rather unstable position. It wants to get an electron, and it wants to form a bond in order to reduce that negative charge, or to bring it to 0. So essentially this, another term for that would essentially be calling it a nucleophile, and it is, as a result, a Lewis base. And in order for this reaction to occur, this would also have to be treated as the Lewis acid. So when we actually conduct this reaction, we know that for Lewis bases, the electron in the Lewis base will transfer over to the Lewis acid in order to obtain a proton. So that is exactly how we will draw it. So when the hydroxide forms a bond with that hydrogen, you also break a bond, the sulfur hydrogen bond. The electrons that were originally in that bond move over to the sulfur, and this satisfies the needs of the Lewis acid as well, because the Lewis acid is considered as a electrophile, so it wants more electrons. So that's what's occurring in this process. The nucleophile, the Lewis base, the hydroxide is trying to get another atom, and that's indicated in the name nucleophile, because you are seeking for another nucleus or another atom. So the resultant products of this would be, along with the spectator ion, we get the conjugate base of the original Lewis acid, and the sulfur atom, because it has an additional pair of electrons now, is negatively charged. In addition, the hydroxide has now obtained a hydrogen, allowing it to form water, which in this case would be the the conjugate acid. So here we can put all these products in these boxes, and we see that the first one is a conjugate base, and this is a conjugate acid. So now the question is to indicate the direction of the equilibrium. And equilibrium always favors the direction always favors the weaker acid and the weaker base. So in order to solve this, in order to determine this direction, all we need is one piece of info. We need to determine whether one of the acids is weaker or one of the bases is weaker, because once we determine that, we can determine which one of their counterparts, so the conjugate acid or the conjugate base or the Lewis acid, Lewis base, whether all of that is weaker or stronger. And I will explain what I mean when we continue. So now that we have, so let's first examine this anion right here, the conjugate base. So this anion as compared to the Lewis base, right? When we look at these two, we find that the anion, the sulfur anion, the base containing the sulfur anion, is actually resonance stabilized. And that's because of this carbonyl group that is adjacent to it. This sulfur the lone pair on the sulfur can move and form a double bond between the carbon and the sulfur, causing one of the electrons in the double bond for the carbonyl group to move up to the oxygen, which produces a negatively charged oxygen. I'm not going to draw the resonance structure, but using the same principles that we have used in the previous problems, you can easily get that resonance structure. But our main insight from this is that this is resonance stabilized. When you look at the hydroxide structure, it is not resonance stabilized. And this presents this allows for you to produce a clear distinction between the two bases. Because if this is not stabilized, then that means that when compared to the resonance stabilized one, it is actually less stable. It is a stronger base. And that means that this structure, the sulfur structure, is actually the weaker base. So we know, in a sense, that this is the weaker base. So now, as I said earlier, once you have one piece of info, all the other pieces fall in place. Since we have determined that the conjugate base is weaker, we know that since this Lewis acid corresponds to this conjugate base, that means that this is the stronger acid, based on the principle that the strength of acid depends on the weakness of the conjugate base. So by evaluating that, by using that principle, we also find that this is the weaker acid, and hence the direction of the equilibrium is to the right, since both of those are weaker. Moving on to the next problem. We find that we are given a molecule and we're asked to draw the most important resonance contributors. So our starting point in determining the resonance structures is this negative charge. And our goal is to try to delocalize or move around that charge without changing the connectivity of the atoms that are already in that molecule. So to help us out with that, I'm just going to draw out the hydrogen atoms. Often when students draw out the resonance structures, they might draw out resonances, what they believe to be a resonance structure, and end up changing the connectivity, because if you move electrons around, you can't move the electrons around in a way that it violates the octet rule. So there are two directions in which this negative charge can move. It's to the left or to the right. Let's start with the left. So I'm just going to add that lone pair to the nitrogen and the two lone pairs to the oxygen. And if we move to the left, we find that the electrons ultimately, the lone pair forms a double bond, and the electrons in the double bond between the nitrogen and the carbon move on to the nitrogen and give us a negatively charged nitrogen. So when we draw that resonance structure out, we get the following. We got that nitrogen with 2 additional lone pairs and that hydrogen, the additional lone pair, and we get that double bond. So we have one resonance structure so far. Now let's try going from the right. So if I was to just remove those previous annotations and we move to the right, then what we find is that there are 2 possible, so once we move this lone pair to form a double bond, there are 2 possible ways this double bond can move. It can either move to the carbon, one of the carbons that it's attached to the carbon that's above it, or the carbon or to the next bond to form a double bond. Let's start off with the first path. Let's move this double bond to that adjacent carbon. And when we do that, let me redraw that. We do that. We get this structure. And this tells us, we might think that it's the end, but as I said earlier, there are 2 possible routes that we can go down. Since we have this set of lone pairs, we can still move it around without changing the connectivity. So let's move this lone pair down here, and when we do that, in order to prevent the octet of this carbon from being violated, we need to move this double bond up to this oxygen. When we do that, we get the following resultant structure. So we are left with 3 resonance structures. And in order to determine the major contributor, we need to look again at the atoms that negative charge is on. So for the first one, this compound, we find that the negative charge is on the nitrogen. For this compound, we find that the negative charge is on a carbon. For this one, we find that the negative charge is on an oxygen. Since carbon is the least electronegative, followed by nitrogen, and oxygen is the most electronegative, and by the rules of resonance, we know that the negative charge of a resonance structure is best suited for the most electronegative atom. And this gives us the lowest energy configuration, and hence the most important resonance structure. So that means that this is the major contributor. And that gives us our final answer for number 8. For number 9, we are given the following molecule, and we are given a series of questions about it. So for the first question, it asks us to determine the hybridization of each atom. But before that, I want to draw the resonance structure of this molecule. So I'm going to ignore this part, and I'm just going to draw everything after that squiggly line. So once I draw that, I draw the oxygen, and then I draw the CH2, followed by the carbonyl group. Well, before I continue, I should probably talk about where my electrons are moving. So the negative charge on this carbon, caused by that additional lone pair, can be delocalized when we move that lone pair to form a double bond between the carbons, and that causes the double bond between the carbon and the oxygen to break, and that lone pair goes to the oxygen. This gives us the following resonance structure. So this will be relevant in our discussion of the hybridization. But first, let's solve the easy cases. So we know that for this carbon right here, it has two electron domains. The first is the single bond, and the second one is the triple bond. So we have two electron domains, so that gives us an sp configuration. When we look at this carbon is connected to 4 atoms, right? It's connected to 2 hydrogens, 1 carbon atom, and 1 oxygen atom. So it has 4 electron domains, so this gives us a hybridization of sp3. Now here's where things get tricky. For this section, we have an oxygen atom which has a different number of electron domains for each resonance structure. For the one on the left, we see that there are 3 electron domains. There are 2 from the 2 lone pairs and 1 from the double bond. For the one on the right, there are 3 lone pairs and 1 single bond, so there are 4 electron domains. And for the CH2, on the rightmost CH2, we see that this is a similar scenario. There are 4 electron domains on the left side, and there are 3 electron domains on the right side. So the question is, which one should I actually write down? But this ties back to the question of hybridization. Hybridization is attempting to lower the energy of the molecule, right? So we want to find the configuration that gives us the lowest energy. When you have lots of lone pairs, that increases the energy of whatever atom you're focusing on. So what you want to do when you're in this situation is you want to try to find the configuration that gives you the least number of lone pairs possible and the most number of double bonds or other types of bonds. So when we have that principle in mind, when we compare these two, we find that for the right, there are 3 lone pairs and just 1 bond, right? 3 lone pairs and 1 bond. But for the one on the left, there's 2 lone pairs and 2, or a double bond. So what this means is that the right side, the oxygen on the right configuration or resonance structure, is actually at a higher energy. So that's not what we're looking for. We're looking for a low energy. And that means that the oxygen on the left side is the preferred configuration. So that means that when we actually consider the hybridization, we'd be considering the geometry of the configuration on the left. So with that in mind, if we see that since there are 3 electron domains, that gives us a configuration of sp2. Using the same principle, we can also find the hybridization for the CH2 group. Since the CH2 group on the right has no lone pairs and only a double bond, this is the lower energy configuration as compared to this. So that means that we should be looking at this configuration. So since there are 3 electron domains, that means that the configuration for this carbon atom is sp2. So with that, we have solved part A. For part B, it's asking us for the bond angle for this portion of the molecule. But we know that the angle of these, if we just have 3 points, space, the angle of those 3 points, and we have a line as such, I'll just label them A, B, C. The angle is determined by the geometry, essentially, of this vertice, or this point. And that means when you connect it back to this situation, it means that we are trying to find the geometry or the angle at this point B. That means we have to consider the hybridization at point B. So the hybridization of point B is sp3 because Y has four electron domains, right? Two bonds with hydrogen, and one bond with carbon and one bond with oxygen. So that gives us an sp3 configuration or hybridization at atom B. This also means that the geometry is a tetrahedral geometry, so the bond angles are 109.5 degrees. So this gives us our answer for part B. For part C, it's asking us about what types of hybridized orbitals form the sigma bond between A and B. So as we had already spoken about in the previous part, part B is sp3 hybridized. Part A, when we look at it, is just sp hybridized because it only has two electron domains, the triple bond on the left side and the single bond on the right side. So that means that that sigma bond in the middle is formed from an overlap of these two hybridized orbitals. So our final answer is just the overlap between these two orbitals. For question number 10, what we're trying to do is we are trying to evaluate the least stable conformation of 2,3,4,5 tetramethylhexane. So for this molecule, what we have to do first is we have to number it, essentially. So in order to do that, we would have to identify the main chain of this molecule. And due to the particular shape of this molecule, there are many different options we have. We can say we can choose this as our main path, or we can choose this, or this. It really doesn't matter, but for the sake of simplicity, I will just choose this as my main chain. So when we do that, we can number from any direction because one, we have methyl substituents and they're all evenly distributed. We find that if we number the atoms, we find the C3C4 bond that the question is asking for. So it's also asking for the least stable conformation. But we know that if we just orient this molecule in a certain way around that C3C4 bond, we can get a very unstable conformation. And as you can probably tell, that occurs whenever the bulkiest groups are interacting with each other, or when they are directly eclipsed over each other. So if we tilt this molecule just a little bit in order to make the C3C4 bond vertical, what we find is that we can draw it out like this. And we know that really the least stable conformation occurs whenever these two bulky groups are actually very close to each other. So after you do a little bit of rotation or conformation, you get when you do a little bit of rotation, you can get a new conformation that is energetically unfavorable. So there is that additional steric repulsion that is present. And if you include the hydrogens in this line angle formula, if you bring them back in, you can see the following structure. I'm using wedge dash notation here to make it more clear, to make the geometry more clear. So with that in mind, we can draw our Newman structure now, because if we look at it from this line of sight, if we were to look straight through this bond like this, then we can draw the following Newman structure. This is a staggered Newman structure because all of these are eclipsed, right? As I had mentioned earlier, when they're aligned, that causes the most steric repulsion. So in drawing these structures out, we end up with this as our final Newman projection. All of the groups are completely, so these two isopropyl groups are totally eclipsed, these methyl groups are totally eclipsed, and that causes a lot of steric repulsion, causing this to be the least stable conformation of 2,3,4,5 tetramethylhexane. For number 11, we are given a cyclohexane ring with two substituents, an ethyl and a methyl substituent, and we are asked to draw the two chair conformations of this molecule. The substituents are in a cis position, so they're both on the same side of the molecule. In this case, both of them are coming out of the page. So that means that whenever we draw it, we have to make sure that they are both facing up when we draw the 3D structure. So let's go ahead and draw those structures out. For the sake of space, I'm going to draw them out here, outside the boxes. So let me draw the chair conformation first, right? That is the most stable position for a cyclohexane ring. So let's say that we have from at point 1, so let me just number these out so it becomes more convenient. 2, 3, 4, wait, no, that's a little bit confusing. 1, 2, 3, 4, 5, 6. So we do that here as well. 1, 2, 3, 4, 5, 6. So when we draw these structures out, let's say that for one, since there are two hydrogens there, let's make the first one axial up. So axial up, that means that for the substituent that's facing downwards, it would be equatorial. And now since we're talking about 6, it would be this carbon right here. So let me just remove the numbering now, actually. Oh, this causes an issue. Let me just try to draw over it. So I'm going to to make it simpler, I'm just going to denote this as the ethyl substituent, ET, and the methyl substituent as such. So when we draw it, since this is axial up, the next axial position is down, up, down, up, down. So since we are looking for two up positions, we want to make sure that the equatorial position on atom number 6 is occupied by that ethyl group, and the axial position is the hydrogen. And for number 5, the axial position is the only up position that there is. So for number 5, we put a methyl there, and we would put a hydrogen there for the equatorial position. And then we can just fill out the rest of the molecule as follows. So what we see here, the other hydrogens are not our concern, is that both of these are, one of the ethyl group is in the equatorial up position and one is in the axial up position. So just keep that in mind. For the next conformation, this time I will not include the numbering. It's the same numbering as last time. I will instead, we'll do a ring flip. So when we do a ring flip, as you might have learned in class already, all the axial positions become equatorial positions, but they don't, whatever group was already up stays up, whatever group was already down stays down, but they just change from axial to equatorial. So in this case, when we do that ring flip, what we find is that, because that's what they mean by two chair conformations, it's just one of the two results of a ring flip. So what we get is that we can start off with the equatorial up and axial down, right? So it was originally axial up, now changed to axial up, now changed to equatorial up. And similarly, this was equatorial down, this changed to axial down. So when we apply that same principle to all the other ones, let me just remove that annotation. When we do that for the other ones, we get the final structure like this. The ethyl substituent is now axial up, and that hydrogen now becomes equatorial down instead of axial down. And for methyl, we now get equatorial up instead of axial up. And I'm just going to fill out the other ones, just to be thorough. So, as I had mentioned earlier, let's ignore all the other hydrogens and everything else. And so we've drawn out the two chair conformations. But now the next question is circle the most stable conformation. So what we need to remember here is that when we are looking at these conformations, we're trying to make sure, especially if they have substituents that are not hydrogens, we are trying to do our best to avoid an issue called 1,3 diaxial interaction. And that is simply whenever if a non-hydrogen substituent is in an axial position, it is capable of actually interacting with the hydrogens that are in an axial position 2 carbons away. So that is what they mean by 1,3. So let's say, for example, let's take this one, this conformation as an example. If we label the carbon that this ethyl group is attached to as 1, then the 2 carbons down, what we find, so let's say from this direction, we find that there is a hydrogen group that is in axial up position. And if we go from the left direction, we also find there's a hydrogen group in an axial position, axial up position. And since all 3 of these groups are in an axial up position, that means that they are actually, there's actually steric repulsion between these 3 groups. And that is energetically unfavorable. It is a high energy conformation. So that means that it causes the molecule to be less stable. And when we look at both of them, really, both of them have 1,3 diaxial interaction. See, in the right conformation, the ethyl group is the one that's undergoing 1,3-diaxial interaction. But when we look at the structure on the left, the methyl group is actually the one that is undergoing 1,3-diaxial interaction. So the question then is, which diaxial interaction is stronger? Which one causes the molecule to become less stable? Well, it turns out that the molecule on the conformation on the right is actually the less stable one, because the ethyl group is a bulkier group. It's larger, it has one more additional carbon and a few more hydrogens. So this causes there to be stronger steric strain or stronger repulsion between that group and the hydrogens that are also axial up. So that causes this conformation to be less stable. But the question is asking for the more stable one. So this leaves this conformation as the most stable conformation because it has less 1,3-diaxial interactions. So that same explanation is what you basically explain here. Reduced 1,3-diaxial interactions for the conformation on the left. For question 12, we are given a set of reactions and we're asked to provide the electron flow associated with bond breaking and bond forming. So to do this type of problem, what we have to first consider is that we have to look at the final product, and that will give us a hint about how the electrons flowed. So when we look at these two products for the first step in part A, first reaction step, what we find is that there is an isolated bromine. So that means the only way it could have got from the reactants to that point, so there was a cleavage at this point, right? And at the same time, we also find for this product that there is an additional ethyl group here. So that means that there was a bond formation, right? So that means that at one point a pair of electrons came from this reagent to this reagent and it formed a bond. So now we have an idea of where what direction the electron flow went. So this lone pair of electrons is our starting point, since that will allow us to form the bond. So since we see this pair of electrons, we have to think, well, which carbon is it going, or which atom is it going to actually attack? So since we know that this bromine becomes isolated, obviously the lone pair is not going to attach to the bromine atom. We do know, however, that we end up with the ethyl substituent attached to this group. So that means that the only way to do that is if this lone pair of electrons actually attaches to this carbon. And when it does that, it forms a new bond, right? But when you make a new bond, you got to break a bond at the same time. And that's precisely what happens. This bond between the ethyl group and the bromine for the second reagent is broken. And the electrons flow from that bond to the bromine. And that explains why we have 4 lone pairs on the bromine. So that is the first set of electron pair movements. So those arrows that you see are the first set of answers to that. Now for the second part, now we're looking at the second and third parts of this reaction. So now we have that isolated bromine. Let me erase the annotations for that. So now we have this isolated bromine, and we have this new formed cation on the left. So how do we go from here from here to here. So when we look at the products, we find that there's HBr. So that means bromine took a hydrogen from the cation. So looking at that molecule, the only possible hydrogen that it could have taken without that would allow for this cation to go to this cation is the hydrogen up here. Because when it takes this hydrogen, it causes this bond to break. Remember, make a bond, then you break a bond. So this pair of electrons moves to the nitrogen, and that causes the formal charge of that nitrogen to go from positive back to 0. So that gives us our final result. So these arrows essentially serve as the final answers. Sorry, let me just redraw that. As the final answers to part A. For part B, we see something a little different. We don't see the formation of two compounds, but we see rather the formation of some sort of new agglomerated molecule. So we know that one molecule had to transfer something to another molecule to form a new bond. So in this case, that would be we see that there is a negative charge here, and there is a positive charge here on that nitrogen. So that could only be the case if the oxygen had to receive another lone pair, and if that nitrogen lost its lone pair by forming a new bond. And that is precisely the case. So when we draw this molecule out, let's just start off with the nitrogen, this lone pair. So for a compound like this, since the oxygen is electronegative, it takes electron density away from the molecule, right? From the rest of the molecule. So that causes there to be a partial positive charge at that carbon. This means that it is somewhat electrophilic. It wants electrons to account for that partial positive charge, to compensate for that. And where is that source of electrons? It's that source of a lone pair. So the nitrogen will react to the carbonyl compound, sorry, let me just edit that, by reacting specifically at that carbon, the carbonyl carbon. So the electrons will flow from there to the carbonyl carbon and then to the oxygen. And that causes there to be, again, that additional lone pair on the oxygen, which will give us the negatively charged oxygen in the final product. So it is this movement of electrons as shown by the arrows that give you the final answer. We reach the final question of this exam, and it is to find the delta H of this reaction using the bond dissociation energies given in the table below. So to find the bond dissociation energy, we are basically trying to, there's actually an equation we can follow, and it is simply that it is the energy of the bonds broken minus the energy of the bonds that are formed. So in order to actually to reach this formula in a sense, we have to first identify what bonds are actually being broken and which bonds are being formed. So when we see the chemical formula, we see two things, or actually a few things. We see that this bromine, this diatomic bromine molecule, is broken, and one bromine goes to this substrate and it forms this compound. Another bromine reacts with the hydrogen to form HBr. So we see that essentially the first type of bond cleavage or breaking a bond is the Br2. So let me just list these out. So bonds broken bonds, yeah. So the first one would be just the Br-Br bond. The second bond that would be broken in this case would actually be a CH bond, and not just any CH bond, a tertiary carbon and a hydrogen. And the reason why this is a tertiary carbon is because it's attached to 3 carbons, as you can see. So there is a cleavage at this point. So the next type of bond that's broken is a tertiary. I'm just going to denote it as tertiary carbon, TC, and a hydrogen. So these are the 2 bonds that are broken in this process. The bonds that are formed, however, lead to the products. So we find that in the product there is a new CBr bond formed, right? And again a tertiary bond and a bromine. So tertiary carbon and a bromine. So that's the first bond that we see. And the next is you can easily see it from one of the products itself, right? HBr. That was not formed earlier. So we're left with these final. We get these 2 sets of bonds, and if we look at this table, actually, let's try to find the values for the bromine-bromine bond. The bond dissociation energy is actually 46 kilocalories per mole. For the tertiary carbon and the hydrogen bond, that is 91. So those are the bonds that are broken. So when we write it down in our equation, we see that that is 91 kilocalories per mole plus 46 kilocalories per mole, the total energy of the bonds broken. And now we have to find the total energy of the bonds that are formed. So the bonds that are formed are the tertiary carbon and the bromine and HBr. So the tertiary carbon and the bromine, as from the table, is 65 kilocalories per mole. The energy of the HBr bond is 88 kilocalories per mole. So adding these 2 together, we get the total energy of the bonds of bond formation. So that is 88 plus 65 kilocalories per mole. And this gives us a total final answer of minus 16 kilocalories per mole. And from this enthalpy of reaction, the standard enthalpy of reaction, it tells us something. It tells us that we are essentially losing energy in this process, right? It's an exothermic reaction. And what does nature want to do? It wants to go to the lowest possible energy state. So through an exothermic reaction, although thermodynamically speaking, other factors such as entropy and temperature also can affect whether a reaction is favored at equilibrium. In this case, the delta H tells us that the reaction favors the products, because by creating more products, what are you doing? You're essentially releasing more energy, and that causes the system to be in a more favorable state, energetically speaking. So this leaves us with products as our final answer. And with that, we have completed the exam. Now we start doing the multiple choice questions. So these are, again, a few of the questions that I found from the ACS Organic Chemistry Review for the ACS Organic Chemistry exam. So I believe these cover different subjects for the first midterm. And Danny will actually cover more of these multiple choice questions as well tomorrow. So there will be a little bit of diversity in how we, what types of questions we do. But let's dive in. So for the first question, it asks us to rank the following compounds in order from the strongest to the weakest acid. So right away I can see a lot of carbonyl bonds, right? Or just of double bonds with oxygen. It's not necessarily carbonyl, but there are double bonds with oxygen. So that gives us a hint that we will have to use resonance to evaluate the acidity of these compounds. So let's go ahead and just draw out the resonance structures for these. The first thing that we will do is that we will start off at compound 1. Let's draw the conjugate base of this. So once it has lost an electron and receives a pair of electrons at the oxygen atom, that oxygen atom will become negatively charged. So just drawing out this structure. So this is our conjugate base. So right away I can say that there is definitely resonance stabilization. And that one resonance stabilized form if we move the electrons here, that causes the electrons in the oxygen, in the carbonyl neighboring that oxygen to move up. And that causes that oxygen to be negatively charged, while this oxygen receives a formal charge of 0. So that is one resonance structure. So I'll just note that down. One resonance structure. Now let's examine another one. So this is just the first one. So let's try out how about we examine the third one actually. So moving this down a little bit so I can have a little bit more space. So we get a very similar molecule, but in this case there is a sulfur atom in place of the carbonyl carbon. So, and just to make life a little simpler, I'm going to denote this group as a propyl substituent. Because there are 3 carbon atoms. And I'm drawing out the conjugate base, so it has lost an electron. So let me add the 2. Since sulfur has, okay, so here is where it gets a little tricky. In order for sulfur to be electrically neutral as is shown in the molecule, it needs to have a formal charge of 0. And in that case, it needs to have an expanded octet, because as you can see from the structure that I've drawn, it's actually having, instead of the usual 8 electrons, it's having 10. And you might be wondering why. And it's because sulfur is a third row element. Sorry, no. It's not within the second row of the periodic table. So yeah, so it is within the third row, but it causes, since it is in the third row, it has a special ability called hypervalence. So it's able to be, it's closer in energy to d orbitals, so it has the ability to actually access some of its d orbitals to take in additional electrons. So that means that it has the ability to have an expanded octet. So it can violate the octet rule. It can have more than 8 electrons that it's bonded with. So that means that in this case, this is a perfectly allowable structure. So I just wanted to make that clear. So now that we have the structure, let's try to make some resonance structures. If we move one of these negative charges from the negative oxygen to here, we get the following structure. So in this case, there's actually there's two oxygens that are electrically neutral. There is no formal charge. So what does this mean? How is this allowed? Because again, hypervalence. The sulfur atom, because it has access to d orbitals, it can accommodate up to 10 to 12 electrons in its bonding. So instead of the usual 8. So that means that we also have a resonance structure here. So, because this is it's really easy to just miss this, but if you keep this in mind, you'll be able to solve the problems easily. And also, there is a negative charge here. Why? Because oxygen has 6. If you look at the periodic table, it has a valence number of 6. So that means that since there are 7 essential connections with the sulfur atom, this causes there to be a negative formal charge. 6 minus 7, negative 1. But we're not finished yet. Since there is a negative charge in the sulfur, it can also be delocalized again to the neighboring oxygen atom. So if we do that, what do we find? So let me just go ahead and move it. That lone pair is that we get the structure. So we actually get 3 resonance structures. For the third case, for the second case, since we have already handled the first and second and third cases, we can examine the third case, where we have a sulfur atom that is actually double bonded to 2 oxygen atoms and also bonded to a hydroxyl group along with a propyl group. So now let's try to evaluate the resonance structures of this particular compound. So again, I'm using propyl for the left-hand side of the compound. When we do that, we can see this structure. I'm just writing it out, expanded, so we can get a better idea of where the lone pair electrons are. So again, we're dealing with a conjugate base, so actually we should add a negatively charged oxygen there to denote that it has been deprotonated at that site. So now let's try to evaluate the resonance structures. So when we move around the negative charges, we find something different from the previous example. In the previous example, I was able to put a negative charge on the sulfur, but that was only because it didn't exceed past 12 electrons. Even sulfur has a limit, right? It has an expanded octet, but it can only go up to so much. And in the case of sulfur, it can go up to 12 electrons. So in this case, there are already 12 electrons bound to that sulfur atom. So this limits our choices. So really, what we have are two additional possible resonance states. So if I was to move this negative charge here and move it up there, I would get the following structure. And similarly, if I did that actually in the other way, if I moved a lone pair from here and caused an electron to go up there, these electron flows, these 4 electron flows don't occur at the same time. The top ones are for the first resonance state, the bottom 2 are for the other one. We can get that was a little too complicated. If instead I just drew out the oxygen, we could actually do it here. We can do the electron flow here. So if I was to move an arrow here and then an arrow up here, what I find is that we get one more resonance state. So what I had meant earlier when I said that there was only one resonance structure, actually no, when I meant there were 3 resonance structures, is that it was including the original state. So if I was to just include, this would actually be 2 resonance structures. My apologies. So now that we have 3 possible resonance structures for that third state, and looking at the second state, we find that there are also 3 possible resonance structures. So when we see that there are 3 possible resonance structures, this gives us a little bit of a conflict, right? How are we going to compare the two? But what we find, actually, is that if you remember from the previous example, there was a negative charge on the sulfur at one point, right? There is no negative charge on the sulfur in any of these resonance structures. And what this indicates is that this structure actually has all the negative charge is delocalized only on the most electronegative atoms. It's never delocalized on a sulfur atom. So since there are 3 resonance structures in both, but one has the negative charge on the more ideal sites, so the more ideal site would be the oxygen atom in this case, this would leave the conjugate base of structure 2 as the most stabilized structure. So that means that this would be the most acidic structure. So that already leaves out B as our final answer. But just to look at the other two, the follow-up to number 2 would be number 3, since there is still 3 resonance structures there as compared to 1, which only has 2. So that gives us B as our final answer. For the next problem, it asks us for the most stable conformation of cis-1-bromo 3-methyl cyclohexane. When we look at this molecule, Remember, again, as I had mentioned earlier, the issue of 1,3-diaxial interaction is something that you really need to consider when you're evaluating the stability of a cyclohexane molecule and its substituents. So when we look at this, we find that in part A, the methyl group and the bromine group are both in the axial position. This is very bad and unstable because of 1,3-diaxial interaction. The methyl group is interacting with the bromine group, but it's also interacting with a hydrogen that is in an axial position 2 carbons away from both of them. So there is a lot of steric repulsion at A, so that is not the right answer. In B, in C, the situation is a little better in that the bromine is in an equatorial position, so it doesn't experience 1,3-diaxial interaction, but the methyl group still does. So that's also not a good choice, but we'll just leave it there. For part D, it's a similar situation, but the bromine this time is in the axial position. So now let's see if, when we look at B, we see that both of them are in the equatorial position. This is the ideal state because at that point there are 0 1,3-diaxial interactions. So this actually leaves the molecule in the most stable state, the most stable conformation, because there is no steric repulsion caused by that issue. So that gives us B as our final answer, and it rules out all the other answers. For this problem, it's asking us to evaluate the sites where the negative charge on this carbon atom can be delocalized to. So where that can move to via resonance. So let's try drawing this out. So I have this molecule here, draw in the double bonds, draw in the CH2, which has a negative charge due to that lone pair. Then I draw the remaining part of this molecule. And let's say that we move this lone pair here. Well, now that we have this lone pair here, which is going to form a double bond, we have to move this double bond here as well to another location in order to prevent the octet rule from being violated. So we have two choices. We can either move the double bond here, or we can move it here. But the question is asking about which sites the negative charge can be delocalized. So since we can move it here, this is an indicator that 2 is actually a possible site. It is a site. So that means that options B and C are incorrect. We can say that right off the back. So let me just edit this. So once we have added this double bond here, we have an additional pair of electrons here. That gives us a negative charge, and when we add the remainder of the molecule, it gives us that extra resonance structure. So we basically are small change. So that's our first spot, so 2. Now let's try moving this electron again. So if I move this electron down here to the next CC single bond, now this double bond has, again, 2 choices just like in the previous issue. But since we're talking about where the negative electron, which carbon can have a negative electron, we want to move it here. That's our next possibility. So let us do that. When we do that, we get the following condition. So now we have 2, 4, and it's time to see whether or not we can, oh, I forgot to add that extra double bond. Now it's time to see if we can get it to 6. So let's try. When we move this extra pair of electrons down, it's very tempting to think that you can go ahead and move this pair of electrons up here. But what you have to realize is that that will remove the connectivity of the molecule. Why? Because if we have because the issue that we have is that if we move that, let me just undo that. Okay, so if we move this double bond up here, there will be no fourth bond at that point. So that will actually change that will cause an unwanted charge separation, and that is not that's not what we want. So we can't go in that direction, actually. Oh no, okay, let me just undo it. So our options then are to move it downwards. So when we proceed to do that, oh no. Okay. We can move this pair up here, down there, and we get an additional resonance state. So it's still not finished yet, though, because we can still move this electron around, this additional lone pair. So if we do that, there's still one more option for us. We can move it down here to form another double bond, and this double bond can move up here to form a negatively charged carbon. And that gives us our final resonance structure. This was a lengthy problem, but in a real exam setting, you would just use the process of elimination to get to your final answer, which would, you could either get to A and D. So this is how we eventually get to that final point. So we have reached our final 2 problems of this review session, and these 2 problems are pretty simple, but they do cover important concepts that you need to really have in your mind, and these are concepts that we have reiterated throughout this review so far. So for the first problem, it asks us to identify a pair of resonance structures. So again, a key principle in resonance structures, and something that you must really drill into your head, is that resonance structures never change the connectivity of the molecule. Never. They don't change what atoms are attached to what atoms. And if you're able to keep that principle in mind, it's easy to evaluate which ones are right and wrong. So when we look at option A, we see that right away that this cannot be a resonance structure, because the nitrogen atom on the right has 2 hydrogens that are attached to it, and on the left there's only 1 hydrogen. So we can tell right away that the connectivity has changed, And same thing for the methyl group, the CH3 group. There is 3 hydrogens there and 2 hydrogens there. So that tells right away that this doesn't work as a resonance structure. C is a more explicit example. We can see easily that a bond is formed here, a bond that was not present here. So again, that doesn't count either. For D, we see that these two structures are again changing their connectivity because there is an OH group here and there's an O group, there's an oxygen here. So it's not like the molecule is flipped either, because what we see is that the CH3 group is still in its position, so that hasn't changed. So really, the connectivity of the molecule did change, so it's not a resonance structure. So what we're left with is just B. And this makes sense because let's say if we wanted to go from the left structure to the right structure, all we would have to do is take an electron from the right, move it here, and then that would cause the double bond, one of the electrons in the double bond, to move to the adjacent bond, forcing this last set of electrons to move to the oxygen. This is what gives us the resonance structure on the right. So ultimately, B is our final answer for that question. For the very last problem, we are just asked to determine what hybrid orbitals are used to form the sigma bond right here. And this is actually a problem that we had a similar problem that we had actually seen in the exam, in the old exam. So when we look at this, we find that for carbon 1, there are 3 electron domains. One caused by the double bond, one caused by the single bond to a methyl group, and another one caused by a bond to a nitrile group. So that means there are 3 electron domains, and that means for carbon 1, the hybridization is sp2. For carbon 2, it's a little different. That carbon is triple bonded to a nitrogen, and it is also singly bonded to a carbon. So since it has 2 electron domains, the hybridization would be sp. So when we consider their overlap and look at the answer choices, we can easily say that B is the final answer. So that concludes our review. Thank you for your time and good luck on your exam.